welcome back to the course of Applied Elasticity. In today's lecture, we are going to talk about one advanced problem on elasticity, which is the solution of a circular disc subjected to diametrical compression. So, we are going to consider one circular disc which is subjected to diametrical compression. So, this kind of arrangement is useful for different types of testings. So, first let us consider this circular disc or circular cylinder which is subjected to the compressive loading P along the y axis. The diameter of the disc is taken to be capital D, O is the center. Now, along the vertical axis or y axis, the disc is subjected to equal and opposite amount of compressive loading P. Now, this particular type of loading arrangement is used, or this particular type of configuration is used in determining the tensile strength for the brittle materials such as rocks, where the tensile test, the commonly used tensile test in UTM cannot be used for finding the tensile strength. So, if the material is ductile, then by making a proper sample using the standards, we can use the uniaxial tensile testing for finding the tensile strength of the sample for the ductile material. However, that method may not be applicable for the brittle materials, because the strength of the brittle materials along the in tension may not be sufficient. So, hence for finding the strength of the brittle material, this is one kind of indirect approach using which the tensile strength can be obtained for the brittle materials by taking it a circular geometry of the material and subjecting it to the compression along one particular diameter. Apart from that, in the photoelastic bench setups also, this kind of samples are used to check the stress patterns using the effect of photoelasticity. So, now let us look into the solution, the stress distribution generated within this body, within this circular disc when it is subjected to diametrical compression with compressive load P. So, this problem we are going to solve using the principle of superposition. We would be considering three different problem solutions and we will be adding them together using the principle of superposition, which would be giving us the solution of the present problem. Now, out of these three problems or three state of stresses, two are called the Flement solution. Now, what is Flement solution? We had discussed this multiple times. The Flement solution is the solution of the stress field generated within an elastic half space when it is subjected to the normal line loading of, let us say, intensity W. So, this is a Flement solution where one elastic half space is considered which is subjected to a uniform normal line loading W at the free surface. Now, for such Flement solution, we have seen that a purely radial state of stress is observed, and along the circular periphery, along any circle touching the point of application of the load, the sigma RR radial stress is constant. So, along this particular circle as shown in the figure, sigma RR would be a constant. So, this sigma RR is constant and other two sigma theta theta and tau r theta are 0 for the Flement solution. So, at any particular point, if you add that to the origin, that is point of application of load, you will only be having the radial stresses sigma RR. This is radial as measured from point, let us say O1, the point of application of load P for these Flement problems. So, all the points, if you consider any point within this elastic half space on this particular circle, it would be subjected to the constant radial stress of a constant intensity, and sigma theta theta tau r theta would be 0. So, this is the first state of stress we are going to consider. Then we are considering another Flement problem, the flipped elastic half space, where the free surface is on the bottom, elastic half space is expanded towards top, and the load P is acting there. So, for this case, let us say O2 is the point of application of the load. So, here we will be having some other sigma RR2. So, let us say previous one is the sigma RR1. Now, for this problem, for the second Flement solution, at any point we are going to have only radial stress distribution like this, which is written as sigma RR2. So, these two Flement solutions are known to us. If we superimpose them and then superimpose a third solution, which is a radial tensile field, which is acting uniformly over the entire boundary of this circle of diameter d. So, diameter of all these circles are d. For both the Flement solution, these diameters are d, which are touching the either point O1 or point O2 for first and second Flement solutions respectively. For third case also, we are considering a circle of diameter d, which is having a state of uniform radial tensile loading of intensity 2p by pi d. Now, I will show that summation or superposition of these three states of stresses will result the required state of stress, that is a disk of diameter d subjected to the diametrical compression of compressive load P. So, here these two Flement solutions only gives us the only includes the effect of the forces acting at top point O1 at bottom point O2. However, even though they are resulting purely radial stress distribution, the superposition of those two will cause a constant compressive strength on the boundary of the disk of diameter d, which is required to be removed by adding the third field of uniform radial intensity tensile load intensity of 2 pi by pi d. So, in addition of these two Flement solution, if you add the third one, that is uniform radial tensile loading state, with that we will be getting the actual or desired state of stress of the disk subjected to diametrical compression. So, let us look into that in details, how this is going to occur. So, consider any point C on the outer periphery of this disk, which is at a distance r1 from point A, that is point of application of P on top, and making an angle theta 1 with the y axis. Similarly, point C is at a distance r2 from point B, which is the bottom point or point of application of the bottom load. Now, with this, with the first solution, for considering point the load P applied at point A, there would be a radial stress coming from the first Flement solution, which will be acting along line A to C. Similarly, considering the second Flement solution, due to the applied load P at point B, the bottom point, due to that another radial stress sigma RR2 would be coming, which will be along R2 along B to C line. So, two Flement solution would be causing two different radial stresses. For the first Flement solution, load being applied at point A, the radial stress would be sigma RR1, which is acting at point C along A to C line, along R1 line, whereas due to the second one, so this sigma RR1 is along AC direction, and due to the second load P applied at point B, sigma RR2 is acting along the BC or along the R2 direction. Now, from geometry we can write that OA, OB, OC, all these are radius of the disk, which is capital D by 2, and considering this triangle ACB, these angle being theta 1 for first Flement solution and these being theta 2 for the second Flement solution, this remaining angle must be 90 degrees. So, theta 1 plus theta 2 should be 90 degree, considering C as a point on the periphery of the disk, and hence we can write that theta 1 is or theta 2 equals to pi by 2 minus theta 1. So, moving forward, each of the Flement solution on these circular boundaries are going to produce a compressive purely radial stress of intensity 2 p by pi d, which is known to us from the Flement solution. From the elastic half space solution subjected to normal loading, we know that the sigma RR is basically 2 times the load W divided by pi r into cos theta. Now, if we are considering such circles of diameter d, cos theta by r can be written as 1 by d, and thus the radial compressive load for each of the Flement solution along the circular boundary would be minus 2p by pi d. So, these sigma RR1 and sigma RR2 both are minus 2p by pi d, both are purely radial stresses, but center for these two radial stresses are different. For sigma RR1, center is at point A, for sigma RR2, center is at point B. Those are the respective points of application of the corresponding load. Now, let us consider capital Tn. This is the resultant normal traction acting on the boundary point C, which is resultant of the sigma RR1 and sigma RR2. Sigma RR1 and sigma RR2 are acting along two different directions defined by theta 1 and theta 2 respectively. Considering the vector resultant of these two, we will be getting this Tn as the resultant vector, and sigma RR1, sigma RR2 both being compressive in nature, both having a negative magnitude, the resultant Tn should also be compressive in nature, should have a minus sign. Thus, if you substitute these two here and use these geometric conditions, that theta 1 plus theta 2 is pi by 2, which would result theta 1 is equals to pi by 2 minus theta 2, or cos theta 2, this can be written as sin theta 1. So, sigma RR1, sigma RR2 both being equals to minus 2p by pi d, the sin square theta 1 plus cos square theta 1 will result unity, and hence the magnitude of Tn, the resultant normal traction acting on the boundary point C, would be minus 2p by pi d. So, the summation of two Flement solutions 1 and 2 due to the two loads acting at top and acting at bottom, in total their resultant is basically a resultant surface traction Tn, and Tn is acting about the center point O. Tn is radially outward from point O, and its magnitude is minus 2p by pi d. As it is having negative magnitude, means it is actually compressive. So, here Tn is basically causing a compressive stress intensity with magnitude 2p by pi d. This is coming due to Tn. So, to include the effect of these two p, the diametrical compressive loads at top point A, at bottom point B, we are taking the help of Flement solution. With that, we are able to achieve, from each of the Flement solution, we are able to achieve the stress distribution effect for top P and bottom P, two compressive loads. But due to these Flement solution, this additional unwanted effect of this surface traction is being added on the entire boundary, which is not actually there in the original problem. So, these compressive Tn of amplitude 2p by pi d is required to be removed, and that we are doing by adding a third state of stress, which is a purely tensile radial state of stress of amplitude 2p by pi d. So, at both the stresses are compressive in nature, that is resulting a normal traction being compressive with magnitude 2p by pi d over the entire boundary of the circular disc, and to remove this we are adding a third state of stress, which is a uniform radial tensile state of stress with sigma R33 equals to 2p by pi d. So, this third state of stress is added with the two Flement solution, with which we can ensure the traction free boundary for the entire disk. So, two Flement solution had captured the effect of the compressive loads applied at point A and B, but additionally gave this Tn, which is compressive, acting along the entire boundary of the circular disc of diameter d. To make the diameter d surface boundary to be stress free, we are adding the third state of stress with sigma RR3 to be 2p by pi d, which is purely radial tensile stress about the center point O. Hence, the superimposed solution of these two Flement solution and this third one, the uniform radial tensile loading, would give us the total solution of the problem. Now, for this third case, for state 3, cylinder subjected to uniform tensile radial loading with sigma RR3 to be 2p by pi d and with sigma theta theta tau r theta to be 0. We can convert it into x and y, the rectangular Cartesian coordinate system, and for that we would have both sigma xx and sigma yy for the third state of stress to be 2p by pi d, that is purely tensile state of stress, and basically all the directions are principal directions here, which is free of any kind of shear stresses tau xy 0. For all the chosen direction of xy, this state of stress is valid. So, this is a kind of hydrostatic state of stress with the hydrostatic pressure value being a positive 1. That is the third state of stress, sigma xx, sigma yy both is 2p by pi d, which is a constant, and tau xy is 0 for this third uniform radial tensile state of stress. Now, coming back to the Flement solution, the first Flement solution due to the load P applied at point A, for which radial coordinate is r1, angular coordinate is theta 1. So, with that we know that the Flement solution sigma RR is minus 2p cos theta 1 by pi r1, sigma theta theta tau r theta is 0. This superscript 1 refers to the first state of stress, the first Flement solution. Now, this state of stress is there for the Flement solution in polar coordinate, which we are converting into the Cartesian coordinate, because it is easy to solve this problem, or it is convenient to represent the result for this problem in the rectangular Cartesian coordinate system, as the load P is applied along y axis. So, using the stress transformation between Cartesian and polar coordinate, sigma xx we can write as sigma RR sin square theta 1 plus sigma theta theta cos square theta 1 plus 2 tau r theta sin theta 1 cos theta 1. Similarly, sigma yy sigma and tau xy, all these Cartesian stress components can be written like this in terms of the polar stress component sigma RR sigma theta theta tau r theta. Now, for the first Flement solution case, we know that sigma theta theta and tau r theta, both of them for the first state of stress are 0. So, neglecting those terms and substituting sigma RR1 as minus 2p by pi r1 cos theta 1, we would be getting sigma xx as minus 2p by pi r1 sin square theta 1 cos theta 1, sigma yy as minus 2p by pi r1 cos cube theta 1, and tau xy equals to minus 2p by pi r1 sin theta 1 cos square theta 1. So, this is the solution for the first state of stress, first Flement solution in rectangular Cartesian coordinate system. Now, similarly, we can obtain the solution for the second Flement problem, that is considering the effect of the P applied at point B, where radial coordinate is r2 instead of r1 and angular coordinate is theta 2 instead of theta 1, with centered at point B. So, using a similar method we can convert the second Flement solution stress field from polar coordinate to Cartesian coordinate, and sigma xx2, sigma yy2 and tau xy2 can be obtained like this. The expressions are exactly same, just r2 is replaced with r1. Now, R1 is replaced with R2 and theta 1 is replaced with theta 2 from the first Flement solution to the second Flement solution. So, now we had obtained the state of stress for all three, two Flement solution in xy or rectangular Cartesian frame and also the solution for the third case, that is the uniformly radial loading acting on the entire cylinder periphery. So, all three solutions we had obtained. Now, using geometry, if you consider the geometry, because theta 1, theta 2, R1, R2 are required to be related. Now, one point to note that here for the first Flement solution, theta 1 is measured in the counterclockwise direction, whereas for the second Flement solution, theta 2 is measured in the clockwise direction. Now, this is not allowed for a specific problem. We cannot take angle to be positive for some part of the solution in clockwise direction and positive to be some part of the solution in the counterclockwise direction. This is absolutely not allowed. So, we have to map our sign convention to a single case. Now, let us choose the direction of theta 2 to be positive, clockwise theta to be positive, and theta 1 direction is thus negative. So, all the angles theta 1 is basically replaced with minus theta 1 because of this, to maintain the uniformity of sign convention. During superimposition of the multiple states, these geometric parameters must be related following the same sign convention. So, then using geometry we can write sin theta 1 is equals to minus x by r1, cos theta 1 is d by 2 minus y by r1, sin theta 2 is x by r2, cos theta 2 is d by 2 plus y by r2. So, replacing theta 1, sin theta 1, sin theta 2, cos theta 1, cos theta 2 in terms of this, in the stress fields we can express all these in terms of x and y for both Flement solution 1 and 2. And R1 and R2, distance of point C from point A and B, the 2 points of application of loads, we can obtain those as square root of x square plus d by 2 plus minus y whole square. This plus sign is responsible for R2, minus sign is responsible for R1. We can obtain both the radius R1 and R2 with the help of this geometry. And note that even though we had derived this equation for a point C which is lying on the periphery of the circular disc, even these expressions are valid for finding the stress distribution within the circle. So, C may not be exactly lying on the periphery, it may be a point here, distance of these C, some C1 to A is R1, C1 to B is R2, and corresponding angles are theta 1, theta 2, with that also this is valid. So, in general R1, R2 are two radial coordinates, it is not compulsory for them for point C to lie on the periphery of the circular disc. So, finally, superimposing all three solutions, two Flement solution and the uniform radial stress intensity solution. If I superimpose this sigma xx, sigma yy and tau xy for the present problem, that is a disc subjected to diametrical compression would be obtained like this. This is the total stress intensity of the present problem which we have solved with the help of principle of superposition, and R1 R2 is given by this formula. Now, if you consider the maximum shear stress generated within the disc, tau max, that we can obtain as square root of sigma xx minus sigma yy by 2 whole square plus tau xy square, because this is a plane stress problem, we are considering a planar problem. So, only sigma xx, sigma yy, tau xy, three planar stresses, in plane stresses are considered. For that, the maximum shear stress generated can be obtained like this, square root of sigma xx minus sigma yy by 2 whole square plus tau xy square. Substituting these expressions of sigma xx, sigma yy and tau xy in this equation, we can obtain the tau max. And then if you plot the maximum shear stress contours for the circular disc subjected to diametrical compression, that would be looking like this. So, at the top and bottom, load P is applied at point A and B. You can see the very large, theoretically infinite stress is caused, maximum shear stress is caused at those 2 points, and all these lines are showing the contours over which tau max is constant. So, these are the maximum shear stress contour. They will be looking like this for the case of circular disc subjected to diametrical compression. Now, considering the stresses along the x axis and y axis, using the resultant state of stress as shown in the previous slide, if you obtain the stresses on the disc along x axis. So, along x axis we can obtain the stresses if you simply replace y with 0, x will remain as it is. So, if you replace y with 0, sigma xx, sigma yy and tau xy, the three stresses can be obtained like this, which are the stress components along the x axis of the circular disc. Note that this is the axis perpendicular to the axis of loading. Here you can see tau xy is 0. So, all the points on x axis are only having sigma xx and sigma yy, but not having any shear stress. Similarly, now if we go for the stresses along y axis, this is the axis of loading. Load is applied along y axis. Both the compressive loads P are applied at point A and B, which is along the y axis. So, along the axis of loading, if you find out the stress components sigma xx, sigma yy and tau xy. Tau xy is once again 0, sigma yy is function of y, and sigma xx would be a constant. So, along the y axis, which is defined by x equals to 0 line, substituting x equals to 0 in the general stress distribution equations, we would be getting x equals to, substituting x equals to 0, we would be getting sigma xx 0 comma y to be 2 p by pi d. Now, this is interesting. So, along the axis of loading, along the y axis x equals to 0 line, we are getting a constant tensile load sigma xx to be 2 p by pi d. So, for all the points on that y axis joining A and B, sigma xx is constant, and these particular phenomena or this particular nature of the stress distribution is used for this setup. This motivates us to use this setup for finding the tensile strength of the brittle material by using the indirect method. So, as this circular disc is having uniform tensile stress 2 p by pi d along the loaded diameter, along the line joining the 2 points of loading of compressive stress. These configuration can be used to check to get the strength of the material, which is used for indirect strength testing for the brittle materials. And along those lines, we have some non-zero value of sigma yy and tau xy is 0. So, in this particular lecture, we had discussed about an important problem of circular disc subjected to diametrical compression, which is solved using the principle of superposition involving the solutions of two Flement problems and another state, which is the uniform radial tensile loading state. Thank you.